All right, percent composition, empirical and molecular formulas. So there's kind of just like before, forwards and backwards. The working forwards is easy, working backwards. A lot of people struggle with it, so you'll just need the steps kind of written out if you struggle with it. So just jumping in. So percent composition means if we're going to look at a component, we want to find out what's the ratio of that component to the overall mass of it. If you just do this number as is, then this number is going to be smaller, right? Because it's a part of this. So that'll give you a fraction. So we multiply by 100 to get usually into the integer range. And so that's it. If we have a sample that it's a 10 grams sample and we find 2.5 grams is hydrogen, the other part is carbon, then if we do the look at the percent hydrogen, we find 2.5 over 10, the part that's hydrogen over the total, we get 25. If we do it for the other part, carbon, we get 75. And then we have an easy check because we can add these up and it should come up to 100, right? We account for everything. And that's the basic idea of percent composition. So in here, it's the same idea, except for now we have three components. So we need to add up all three components to get the total amount of the compound. And again, we have the check where we can add these up and it should add up to 100. So the most of the time though, you're going to be given a formula and asked to solve for it. And so then you just have to be able to read the formulas for it. And so we can have this way where it's more like a structural formula kind of showing you the spatial arrangement in space, or we can have a condensed one where we just have the number of carbons, number of hydrogens, nitrogens, and oxygens. And so you just have to make sure you account for everything. So here there's two nitrogens and add it up. So you're just going to take the amount of mass of everything. And so this is actually a typo. This should be hydrogen here. So we can see there's three hydrogens in ammonia, NH3. And just want to remind you, ammonium and ammonia, so the difference between it. So there's three hydrogens. So we have 3 times 1 gives us 3.024. So this would be the amount of hydrogen over the total mass. So 3 plus 14 gives us 17. So we can get the parts of them. All right. So in this example too, you can come back and go a little slower because I give you the number at the top here that this is from Kim Libre. And we can see from this formula accounting for all the carbons and hydrogens and oxygens. So the carbons, we have 9 carbons over the total molar mass. So you'll do 9 times 12 for the carbon to give you a number and get the percent carbon. If you do the same thing for the hydrogen, you get this and oxygen this. And so now we can see they add up to 100. And so that gives you confidence you did it correctly. I've never seen the case where it adds up to 100 and someone does it incorrectly. So that's your little check for it. All right, so now this is the backwards direction, which some people find a little bit more difficult. And so it's similar to how we started. Consider a sample that has this many grams of carbon, this many grams of hydrogen. But instead of finding the percent composition, it wants to find the corresponding number of atoms, or what we usually say is empirical or molecular formula. So how do we do it? Well, for given grams, then we need to get it to grams to moles. And so you simply take grams and divide by the molar mass to get it to moles. The other form of it is you start with the percent composition and you find the number of grams. And it ends up then what we do is we just say, well, if we're given that it has 1.17% carbon by mass and 2.287, well, it won't come out because it'll add up to 100. But this means percent, we say that what if we have 100 grams of sample, then the percentage is equal to the grams. All right, you'll see some examples in the book But either way, we get it to grams as a starting point, and we get to moles. And it's maybe not obvious to some why moles. Well, remember we did moles to atoms. They all have the same ratios, and that's what gives us then that relative ratio of the amounts of it. So once we get it to moles of the different atoms, then what we do is we would write the formula. It would look like this. And you never saw formulas that look like that before. So in order to get it to integer value, we simply divide by the smallest one. So the one we're dividing by goes to 1. The other one is not the smallest. So you get this nice integer relationship. And this is what we call the empirical formula. It may be the molecular formula, but you need to, it's definitely the empirical, the simplest ratio between them. And so in order to go to a different molecular formula, you need additional information like molecular weight. And often what you find is the weight when you add this up, and it's going to be smaller, and the molecular weight will be some integer times bigger than that. So that tells you how you need to multiply everything to get it. Okay, so you can come back and look at this in more detail. Here is a summary of the steps and the nice graphical kind of figure to help you to visualize it along the way.